Welcome to the exam review of the Indian Actuarial Professions CT3 paper for October 2014. I'm John Lee, a tutor from ACTED, the actuarial education company, which provides study materials and coaching on behalf of the UK and Indian actuarial professions. In this video, we'll give a brief overview of each of the questions on this paper. Whilst we don't yet provide detailed solutions for the Indian papers, we do offer online coaching, revision materials, and study support, details of which can be found at the end of this video. So let's start with question 1. This was a beautiful short bookwork question, which simply requires you to remember the definitions from chapter 1 for each of the types of categorical data, but don't forget to provide an example of each. You might recall this diagram from chapter 1 of the stats pack. Dichotomous data is data that can only take two categories, an example of which would be male or female. Nominal data is data that can't be ordered, for example types of insurance policy, covering fire, theft or accidental damage. And ordinal data is categorical data that can be ordered, for example disagree, agree, strongly agree. Question 2 tests a discrete distribution from chapter 4 of the notes. As is common with these questions, they don't tell you which distribution it is, and they expect you to work it out from the question. We're asked to calculate the probability of examining 10 pens before red pens are found. If you're confused, you can see that a trial is examining a pen, and a success is obtaining a red pen. And so we're asked to calculate the probability that we have 10 trials until our fourth success. This is describing a type 1 negative binomial distribution where k is 4 and the probability of success is 40%. You can now find the probability that x is 10, which will be 0.1003. In part 2 of the question, we've still got a negative binomial, but we're now only examining until 2 successes. So we now have a type 1 negative binomial where k is 2, but the probability of success is still 40%. We're asked to calculate the expected number of claims, so we simply have to find the mean. This is no problem as it's given on page 8 of the tables. The expected value is k over p, or in our case 2 over 0.4, which gives you 5 pens on average. Question 3 asks us to calculate the probability of a sum of numbers, but notice the key word approximate. This tells us that we're going to calculate approximate probabilities using the material from chapter 8 of the notes. Recall that the central limit theorem tells us that the sum of random variables is approximately normally distributed, with mean n times mu, where n is our sample size, and variance n times sigma squared. Well, our n in this case is 200, as we're asked 200 questions. But we don't know what our mu and sigma squared are, we're going to have to calculate those. Since the participant selects the options 1, 2 or 3 at random, that means that they have equal probabilities. We could find the mean and variance from first principles, or we could recognise that we have a uniform discrete distribution and use the formula from page 10 of the tables. Either way, you'll get a mean of 2, e of x squared is 4 2/3, and so this gives us a variance of 2/3. Using t to stand for the total sum, we can see that we now have a normal distribution with mean 200 times 2, which is 400, and a variance of 200 times 2/3, which is 400 over 3. We're asked to calculate the probability that t lies between 380 and 420 inclusive. But don't get caught out. We're going from a discrete distribution, as it can only take the discrete values 1, 2 and 3, to a continuous distribution, a normal distribution, and so we need to use a continuity correction. I always recommend that students draw bars, where each bar goes from 0.5 either side. We want to include the 380 and include the 420, and so that takes us from 379.5 up to 420.5. Since we have a normal distribution, we need to standardise this. We do this by taking away our mean of 400 and dividing by the square root of our variance of 400 over 3. This gives us that our standard normal z lies between plus and minus 1.77535. We can split this up, and then because the standard normal is symmetrical about 0, the probability it's less than minus 1.77535 is the same as the probability it's greater than, which is in turn equal to 1 minus the less than. Altogether, this will give us 2 lots of the probability it's less than 1.77535, take away 1. We can now use interpolation on the tables between 1.77 and 1.78 to get the final probability of 0.92416. For question 4, we have a gorgeous question where we're asked to draw a box plot and then find the interquartile range. You recall that a box plot draws a box between the lower and upper quartile with a line representing the median, and then it has some whiskers, as we call them, which go from the lowest to the highest value. This would have been a very straightforward question. The lowest value is 55 and the highest is 97. In order to find the median, we need the middle value. We have 72 students and the middle value is given by half of 72 plus a half, which is the 36.5th value, which puts it as one of the 74s. There are 2 ways of calculating the lower quartile. I'm going to use a quarter n plus a quarter, which places the lower quartile as the 18th and a quarter value. This is one of the 67s. Had I used the alternative formula of a quarter n plus a half, I would have got the same answer. For the upper quartile, using 3/4 n plus 3/4, I would have got 54 and 3/4 value. This would have made it one of the 81s. Had I used the alternative formula of 3/4 n plus a half, again I would have got the same answer of 81. So we draw our box plot like that, and the interquartile range is the distance between the upper and lower quartile. Subtracting 67 from 81 gives us an interquartile range of 14. Question 5 is where this paper starts getting a little bit more tricky. We're given the MGF of a random variable z, which is itself the sum of x and y. The first 3 marks of finding the mean and variance of z would have presented no problems at all. Recall that if you differentiate an MGF and then substitute in t as 0, you will get each of the moments. Differentiating once with respect to t gives us the following, and substituting in t as 0 gives us e of z, which is 0. Differentiating again with respect to t gives us the following. Substituting in t as 0 will give us e of z squared, which is 1.2. To get the variance, we take away the square of the mean, so the variance is also 1.2. Part 2 is where things start getting a little bit more tricky. We're asked to obtain the marginal distribution of x or y. Well, how do we do that? Well, we're told that z is the sum of x and y. So what we could do is make use of the MGF of z to obtain the distribution of z, and then from there get the distribution of x and y. How do we do that? Well, recall that the definition of an MGF of z is equal to the expectation of e to the tz. For a discrete random variable, which we have here, that will be e to the tz times by the probability that z is equal to z. Well, comparing that with our MGF, we can quickly see that we have t times z here, so z is minus 2, and in front of it must be the probability that z is minus 2, which is 0.09, and so on. Drawing this up in a table, we obtain the following distribution. Now, since z is the sum of x and y, the largest each of x and y can be must be 1, so we get the total sum of 2. And the smallest each of x and y can be must be minus 1, so we get the total of minus 2. Well, so far so good. All we need to do now is calculate the probabilities. Why don't we call the probabilities of A, B and C? Now, the hint in the question is that we're told to use part 1. And in part 1 we calculated the mean and the variance of z. Since z is equal to x plus y, the mean of z must equal the mean of x plus the mean of y. So the mean of x will be minus 1 times a, which is minus a, plus 0 times b, plus 1 times c. And since y is the same as x, we'll have 2 lots of this altogether. Now in part 1 we saw that e of z is 0. So this is 0. That tells us that a must equal c. Similarly, because we're told that x and y are uncorrelated, that means that the variance of z will equal the variance of x plus the variance of y. For x, e of x squared will be a plus c, and then we need to take away the mean squared, which is 0. The same for the variance of y, so altogether we've got two lots of a plus c, and that must equal the variance from part 1 of 1.2. That tells us that a plus c is 0.6, and so a is equal to c, which is equal to 0.3. Since our probabilities must add up to 1, that gives us that b is 0.4. For part 3, we need the joint distribution of x and y. Drawing up a table, we just need to calculate the probabilities. -1 and -1 will add up to -2, and we saw that probability was 0.09. Similarly, in order to get a total of 2 with probability 0.09, there's only one combination, x is 1 and y is 1. So that has probability 0.09. Let's look at another combination, -1. There's only two possibilities that do that. X is 0, y is -1, or the other way round. Since x and y are identical, they must each be 0.12. To get the total of 1, we must have x is 1 and y is 0, or the other way round. Again, that means each of those must be 0.12. Finally, because the probabilities of 1 and -1 are the same, we can get the other corners to both be 0.09, which tells us that the middle value is 0.16. And to finish off this question, we have a simple test of whether they're independent. One way of doing this is to take a combination of x and y. If they're independent, then the probability that x is x and y is y will equal the probability that x is x times by the probability that y is y. For example, the top left-hand corner, the probability that x is -1 and y is -1 is 0.09. The probability that x is -1 is the total of the first column, which is 0.3, times by the probability that y is -1, which is the total of the first row, which is 0.3. And so it works for this combination, and similarly we can see it works for the others. Question 6 tells us about x, which represents claim amounts, and n, which represents the number of claims. And we were asked about s, which is the total number of claims. We can see here that we're describing a compound distribution. S is equal to x1 up to xn. And we're asked to obtain the mean and variance of z. Well, this will be easy to do, as the formulae for these are given on page 16 of the tables. All we need to do is see what distribution x and n have. We're told that x is exponential with mean of theta, and so the parameter is 1 over theta. Unfortunately, there's a mistake in the question. It says that Q is the probability of a claim from an insured population of size W consisting of independent lives. It's a little bit confused what it's trying to say. It doesn't tell us until part 2 that we're talking about life insurance and there's only one claim, in which case we have a binomial WQ. Looking up the means and variances of x and n and substituting the page 16 formulae give the required answers. In part 2, we have to apply these formulae. Since we're told we have 1,000 employees, and we're given the proportion, we can see that the W, which are the number of individuals, are 500, 300, and 200. The Q is the probability of death, and we're given the death count, which is per 1,000. And so our Qs are 0.025, 0.075, and 0.1. And finally, we're told the average benefit, which is theta. We're told that everything that moves is independent. And so if we denote the total claims in group 1 as S1, total claims in group 2 as S2, and the total claims in group 3 as S3, we can use our formulae to calculate the mean and variance of S1, S2, and S3. And because everything is independent, then the mean of S will just be the sum of their means, and the variance of S will just be the sum of their variances. This gives us 347.5 and a variance of 4,313.9375. Okay, what's the question? Well, we want to set a single premium so that the probability that the total claims exceed this is 0.5. Well, how on earth are we going to calculate probabilities? Well, it tells us to use the normal approximation. So the probability that our total claims exceed our premium, which we'll call P, must be 0.5. Using a normal approximation, that's going to be the probability that a standard normal is more than our premiums, take away our mean, which is 347.5, divide by our standard deviation, which is the square root of our variance. Since we're told this is 0.5, we could look up page 162 of the tables, which tells us that the standard normal is more than 1.6449 with probability 0.5. Hence this value here is our 1.6449. Calculating that, you get a P of 455.54. Question 7 is a little bit confusing. We have x1 up to x2n, which come from a Bernoulli distribution. You recall that a Bernoulli distribution can take values 0 or 1, and we're told the parameter is p, so it takes 1 with probability p and 0 with probability 1 minus p. However, we define a new value, lambda hat, which is equal to 1 over n times the sum of zi, where zi are equal to this. Essentially, we are multiplying two of these Bernoullis together. And we're asked to say why this is actually equal to another Bernoulli with parameter lambda. Now, what is lambda? It's not entirely clear, but they're trying to say up here that lambda is p squared. So let's have a look at our first combination in that sum, x1 times x2. If both of them are 1, then their product will be 1. What's the probability of this happening? Well, the probability of each being 1 is p, so we'll have p times p, which is p squared, which remember we've called lambda. Now for any other of the combinations, 0 and 1, 1 and 0 and 0 and 0, it will give us a product of 0. The probability of that happening, well, obviously must be 1 minus p squared, or 1 minus lambda. And so we've shown actually that we have a Bernoulli distribution. There's only two possibilities, and the probabilities are lambda and 1 minus lambda. Next, we have to show that we have an unbiased estimator. Recall that the bias of lambda hat is the mean of lambda hat take away what we're estimating, which we're told is lambda. Now, this is a very common proof and should have presented no problem to candidates. So we just simply substitute in our formula, and then we observe that we can take the 1 over n outside, we can take a summation outside, so we just need E of zi. Now zi we've just said is a Bernoulli, and so we can look up the expectation in the tables. Well, it's not listed, but a Bernoulli is a binomial with n equal to 1, and so its mean will just be lambda. So we'll have 1 over n, sum of lambdas minus lambda, which will be 1 over n times n lambda, which is lambda, and so we get 0. Okay, next we need to find the Cramer-Rea lower bound. Now the Cramer-Rea lower bound is defined on page 23 of the tables. It's equal to minus 1 over the expectation of the second derivative of the log likelihood. Okay, so we need the likelihood first of all. Now the likelihood is the probability of observing our sample. We have a sample Z1 to Zn, and so the probability of observing our sample is going to be the product of them. To get the probability, again we use the fact that the Bernoulli is a binomial with n equal to 1. So using the binomial probability function, we can see that this probability would be lambda to the Z1, 1 minus lambda to the 1 minus Z1. And so on for all the others. Multiplying these together, we see that we'll have lambda to the sum of Zi's, 1 minus lambda to the sum of 1's, which is n, take away the sum of Zi's. Logging this gives the following. Differentiating with respect to lambda gives the following. A common mistake that students make is to put plus here by accident. We're using the chain rule to differentiate the log. We're using the chain rule to differentiate the log of 1 minus lambda. Differentiating a second time gives the following. And so we're now ready to calculate the Cramer-Rea lower bound. We need to find the expectation of our second derivative. To do this, we need to remember that the lambda is a constant, the n is a constant, it's only the zi's that are random variables. And so we can take out our constants and summations, and then we use the fact that zi is a Bernoulli with parameter lambda, and so E of zi is equal to lambda. Cancelling lambda on the first fraction and 1 minus lambda on the second fraction, combining them together gives the following. The Cramer-Rea lower bound is minus 1 over this, which is lambda 1 minus lambda over n. The final part of this question is seeing if the variance of lambda hat obtains the Cramer-Rea lower bound. Substituting for lambda hat, taking the constant outside of the variance, recall that it squares, and we can take the summation out as they are independent. Again, recall that Zi is a Bernoulli, which is a binomial with n equal to 1, so we can look up the variance from the tables, which will be lambda times 1 minus lambda. And hence, summing them, we have 1 over n squared n lambda 1 minus lambda, which is the Cramer-Rea lower bound. Question 8 requires us to obtain a confidence interval. However, we have again another slight twist here. We're told that we have a random variable from a normal population with mean of theta and standard deviation of theta, so variance of theta squared. Well, there are two ways of going about this. The usual way is to use the result x bar minus mu over sigma over root n, which is a standard normal, if we know what sigma is. Well, here we have mu is theta and sigma is theta. Our n is 25, so root 25 is 5. So this will be a standard normal. The critical values will be plus or minus 1.96 for a standard normal, and calculating x bar is 2.7864. And so what we can do is rearrange this to obtain the value of theta. If you do that, you get a confidence interval between about 2 and about 4.6-ish. Alternatively, we could have used the t-distribution, which has the sample variance in it. Since n is 25, we have a t24 distribution, which gives critical values of plus or minus 2.064. Substituting in the sample mean of 2.7864 and the sample standard deviation, which is the square root of 2.55914, we can then calculate the value of theta from this and get a confidence interval which goes between 2.126 and 3.447. Presumably the examiners will give credit for either method. After some of the complicated questions we have, question 9 is just gorgeous. This is a straight down the line linear regression question from chapter 13 of the notes. In part 1, we're asked to determine the fitted linear regression, which is y hat is alpha hat plus beta hat x. Page 24 of the tables gives you the formula for beta hat, which is sxy over sxx. And the formula for sxy and sxx are both also given on page 24 of the tables. This gives a value of beta hat of 0.79058. From page 24 of the tables, alpha hat is equal to y bar minus beta hat x bar. Substituting in the numbers, you'll get a value of alpha hat of 15.6843. Part 2 of the question, we need to calculate an estimate for the error variance. Well, this formula is also given on page 24 of the tables. It's 1 over n minus 2 syy minus sxy squared over sxx. Syy is 1512.875, and substituting that in here, you'll get an estimate of 22.4665. The second part is a little bit more exciting. Obtain a 90% confidence interval for sigma squared. This formula is not given in the tables, but recall from page 23 that n minus 1 s squared over sigma squared is a chi-squared n minus 1, and we can use that to obtain a confidence interval for sigma squared from a standard sample variance. Well, in this chapter, instead of using s squared, we're using sigma hat squared, the formula of which has n minus 2 on the denominator, and so we multiply by n minus 2. This gives us a chi-squared n minus 2. Since n is 8, we have a chi-squared 6. The critical values are 1.635 and 12.59. It's not much bother then to calculate a confidence interval which goes from 10.71 to 82.45. The last part of the question asks us to calculate the proportion of variation, or r squared, often known as the coefficient of determination. The formula is not in the tables, but you might recall that it is the square of the correlation coefficient. Substituting in our values gives 0.9109, This means about 91% of the variation is explained by the model. So don't forget to comment, and so we'd say this means we have a very good fit. Question 10 is a very straightforward ANOVA question from chapter 14 of the notes. First of all, we're asked to calculate an estimate of the overall mean temperature. To do that, you simply have to add up all the temperatures, and the quickest way of doing that is to add up the sums and divide by how many results we had, which is 21. This gives an estimate of 58.714. Part 2 asks us to construct an ANOVA table and then carry out the ANOVA test. The table, you'll recall, looks as follows. The first thing we need to do is calculate the sum of squares. Good news for us, the formula given on page 26 of the tables. SST is equal to the sum of squares, which we can calculate by summing up the sum of squares for each of the electric ions. We then subtract y double dot squared, which is the total sum of 1233 squared, all over n, which is 21. This gives us a result of 4240.286. Next, we'll calculate the sum of squares between the treatments. Using the formula in the tables, we take the sum for each treatment, we square it, and divide by how many results they have in that treatment. Repeating it for all three treatments, we then subtract the overall sum squared divided by the total number. This gives us 3428.72. Subtracting these gives us the residual sum of squares of 811.565. The easiest way to obtain the degrees of freedom is to look at the statistical test at the bottom of page 26. SSB is divided by k minus 1, where k is our number of treatments, which is 3. 3 minus 1, which is 2. SSR is divided by n minus k, so that's 21 minus 3, which is 18. The mean sum of squares is obtained by dividing the sum of squares by the degrees of freedom. Now we have these, we can calculate our statistical test. We do this by dividing the mean sum of squares. This gives us a value of 38.02. This result comes from an F distribution with degrees of freedom 218. The ANOVA test, you recall, is always a one-sided test, and looking up the 5% value, we see it's 3.55. Our statistic is way more than that, and in fact more than the 1% value, and so we have evidence at the 5% level and even the 1% level to reject our null hypothesis, which I've forgotten to state here, which is that the treatment means, or in this case, the mean temperatures are the same. Don't get caught out though. The question does ask you to state any assumptions that you make. The three standard assumptions for the ANOVA test are that we are assuming that the results in each treatment are normally distributed with the same variance, and our observations are independent. The last part of this question asks us to compute an estimate of the underlying common variance in temperature readings. Well, we're given the formula for the variance estimate on page 26 of the tables. It's SSR over n minus k, which is the same as the residual mean sum of squares of 45.087. Question 11 involves maximum likelihood estimation again. We're given an unusual distribution with its PDF and asked to calculate the maximum likelihood estimate. Since we're told to show that it solves the following quadratic equation, at worst, if we couldn't get it, we could take this result and use it in the later parts of the question. The likelihood for theta is the product of the PDFs. Substituting our given PDF gives the following. Simplifying this gives the following. Our second step is to calculate the log likelihood. This gives the following. To obtain the maximum likelihood estimate, we need to differentiate this with respect to theta. And this gives us 100 over theta plus 100 over theta plus 1 plus the log of the product of x's. Well, using the log rules, log of AB is equal to log of A plus log of B, and so we can sum the logs of each of the xi's. The maximum likelihood estimate maximizes our log likelihood, and so the derivative will be 0. We now have a bit of algebraic manipulation to obtain our required expression. First of all, let's see if we can get k into it. If I divide everything through by 100, I can see that my last term is equal to k to the minus 1. As our required format doesn't have any fractions, we're going to multiply everything through by theta, and by theta plus 1, and also by k. It's now easy to see that we have our theta squared plus 2k theta plus 1 theta plus k. For part 2 of the question, we're given the sum of the logs to be minus 58.334. We can substitute that in here to get our value of k minus 1, and then our value of k. Substituting that into this equation gives us the quadratic that we need to solve. Using the quadratic formula gives theta to be either minus 0.5714 or 3.0000. Since we're told in the question that theta is positive, we must have theta is equal to 3. We're now going to use this estimate of theta to answer the next part of the question. Substituting in our value of theta is 3, we'll get a PDF of 3 times 4, x to the 2, 1 minus x. We want to calculate the probability that this distribution lies between 0 and 0.25. To do that, we need to integrate our PDF. This is quite a straightforward integral, and so substituting the values in gives us 0.05078, which is approximately the 0.051 that we require. To obtain our second probability, we could use the fact that the probabilities should add up to 1, which will give us 0.263. Alternatively, we could have obtained this by integrating the PDF between 0.25 and 0.5. Unfortunately, because of rounding, we would have got 0.262. For the final part of the question, we're asked to perform an appropriate hypothesis test to investigate whether the assumed model fits the data. Seeing whether any model fits the data is asking a chi-square goodness of fit question. We're given our observed frequencies, and our expected frequencies will simply be the probability times by how many results we have. Earlier in the question, we were told there were 1,000. Our chi-squared statistic is the sum of our observed frequencies minus our expected frequencies, all squared, divided by our expected frequencies. Working this out gives us a statistic of 5.56. The degrees of freedom is equal to the number of categories that we have, which is 7, take away 1, and don't forget, because we estimated a value of the parameter on this data, we'll need to take away a further 1. So we have a chi-squared 5 distribution. Recall that a chi-squared goodness of fit test, like the ANOVA test, is always an upper one-sided test. From the tables, the 5% value is 11.07. Our value of 5.56 is way less than that, so we have insufficient evidence at the 5% level to reject the null hypothesis, i.e. the model is a good fit. And now for the final question. The weight of object is measured by an electronic scale, which reports a true weight plus a random fluctuation. And so our results have a normal distribution with mean 100 and variance sigma squared. Similarly, a second electronic scale is also normally distributed around the true mean, but has a variance of phi squared. We're asked to write down the distributions of xk minus 100 over sigma and yk minus 100 over phi. Well, if we take xk and take away 100 and divide by sigma, that effectively standardizes it, which gives us a normal 0,1, a standard normal. And the same thing for the second one. Then says, hence state the distributions of these. Well, what we've done is we've squared a standard normal, which you may recall gives a chi-squared 1. We're then summing these up, and again you may recall that summing chi-squareds gives another chi-squared. So in the first case, v will have a chi-squared 10, and w will have a chi-squared 8. Where do we go from here? We're now asked to state the distribution of u times by phi squared over sigma squared. Well, that would give us v over 10 over w over 8. Well, recall that we said v was a chi-squared 10 and w was a chi-squared 8. And this is the definition of an F distribution with 10 and 8 degrees of freedom. And we can use this as a pivotal quantity as it contains both sigma squared and phi squared. To calculate a confidence interval, we're going to need the value of u. On the numerator, times it by sigma squared cancels with the sigma squared on the denominator of the v definition. Similarly, on the denominator, multiplying by the phi squared cancels with the divide by phi squared in the definition of w. We can calculate these results from our sample data to give us a value of u equal to 3.763. Now we're asked to obtain a confidence interval for sigma squared over phi squared, which is the opposite way round to what we've been given up here. What I'm going to do is instead say that u over sigma squared over phi squared will be our F10(8). The critical values for a 95% confidence interval are 4.295 and 1 over F810, which is 1 over 3.855. Substituting in our value of u, we can then set the statistic equal to our two critical values. This gives us a confidence interval from 0.876 up to 14.5. We're now asked to carry out a hypothesis test at the 5% level. We've already got our value u of 3.763, which comes from an F10(8), which must be this distribution given here. 3.763 lies between these two values, which gives a CDF value of 0.96359. The p-value is the probability of obtaining a more extreme result. Well, we're greater than the median, so we're closer to the upper end of the distribution. So 1 minus this gives us a probability of 3.64%. But don't get caught out. We have a two-sided test, and so the p-value will be double this, which is approximately 7.28%. This p-value is greater than 5%, and so we have insufficient evidence to reject the null hypothesis at the 5% level, and so we would conclude that the variances are the same. In part 5, we have to interpret our result, which we've just done, but with reference to the confidence interval. Well, our confidence interval, you'll notice, contains 1, which is the value if the variances are the same. So we can see that our results are consistent. On the screen now is the address for further information of the Indian products we offer. Or if you'd like to see for yourself, there are links to YouTube videos of a unit from our CT3 online classroom and a snippet from one of our live webinars. Both are available in pounds or rupees from our e-store and come with full tutor support. Thanks for listening.